Good afternoon to everybody. My name is Nicola Gigante. I'm from Italy. I'm a PhD student from the University of Udine. And in the spare time, I love to participate to these community events. I meet a lot with my friends from the Italian C++ community that are here. Hey, hi. And well, today I will talk about functional programming. It's not the main paradigm of the C++ language, right? But we'll see that the language has a lot in common with functional languages, and we can exploit a lot of features to take advantage of functional programming techniques. So what we will talk about? The first question is, wasn't C++ an object-oriented language last time I checked? Well, yes, but it's not the main paradigm of the language anymore. You know, in modern C++, it's not an object-oriented language, not completely at least. And so what's wrong with object-oriented programming in the first place? And what is functional programming? It sounds like the buzzword of the decade. What is functional programming? And then I cherry-picked a few concepts and a few advices, if you want, to write functional style code. And we'll see one after the other. Higher order functions, immutable state, laziness, and take advantage of the type system, and lawful abstractions. Not awful abstraction, but lawful abstractions. Okay. And then we'll take a look at the future, at C++ 17, to see what will hopefully happen. Okay. So let's get started. So C++ supports very well object-oriented programming. We have abstract classes, multiple inheritance, polymorphisms, encapsulation, everything else. And it started as an object-oriented language. It was called C with classes for a reason. But so object-oriented programming is the main paradigm of the language, right? Really no, anymore. And to see why, let's take a look at the standard library, which is the C++ library. We have a lot of classes, of course, but very few classes are meant to be derived. A lot of classes cannot be safely derived because they don't have virtual destructors, okay? There are very few virtual functions meant to be overridden, and very few pure virtual functions. And I can't recall a case of a pure virtual function, so maybe somebody can remember one from the standard library. Most occurrences of virtual functions and classes meant to be derived in the classic OOP pattern mostly comes from IOStreams, which is not the most recent part of the standard library. And so it seems that the committee doesn't know what OOP is because the standard library is not object-oriented, okay? So is C++ an object-oriented language? Yes, if you mean that it supports the paradigm, but no, if you mean that C++ programmers are forced or encouraged to follow the paradigm. But why? Well, what's wrong with object-oriented programming? Well, it is simply not enough anymore because there are a lot of questions, both design questions and algorithmic questions, that object-oriented programming does not answer. How to write and compose algorithms. Object-oriented programming talks about the large scale of software architecture, but when I write an algorithm, it is still the dear old imperative programming paradigm from ages ago. OOP doesn't help us to write and express and compose algorithms. And it doesn't help us to write code that is both high level and fast. Of course, we can do it, but it's not, object-oriented programming does not help us doing this. And then, of course, it completely ignores the problems in concurrency and parallelism. There's simply, it doesn't have anything to say here, okay? So we need more, and C++ programmers know it because they invented a lot of techniques and paradigms that help object-oriented programming to answer to these questions, and generic programming and all of this, okay? So functional programming can be one of the answers, part of the answer to, to these questions. And so what is functional programming? Functional programming it's not uniquely defined. You can ask to an Haskell programmer or to a Clojure programmer or to a Lisp programmer, and everybody will say, this is my personal vision of functional programming, and these are the 4 most important characteristics of functional programming, in my opinion. The first one, that is probably the less controversial, is that functions are first-class citizens. Functions are values that you can pass around and use, like integers or like strings. And you make a lot of things with functions. You play with functions, you have fun with functions. And the second one is immutable state. Functional programming simply doesn't want to mutate variables. And the third, which is strongly connected with the first, is that we want our functions to be pure, because that allows them to be composable, generic, reusable, and we'll see why. And the fourth is an advice to make easy use of the type system of the language. Of course, there are a lot of strongly typed functional programming languages, but also a lot of loosely typed functional programming languages. For example, Lisp or Clojure, which are very good functional programming languages. So users of these languages will not probably agree to the fourth item, but C++ is strongly typed, so this is the kind of functional programming we're looking for. But C++ clearly has not been designed to be a functional programming language, of course. So one could ask me, why care? Why should I spend effort into blend language to program functionally? Well, because the complexity of software is still increasing. It's not going to stop increasing. But even if hardware becomes more faster, and we need to write fast code to take advantage of fast hardware. So we need techniques that help us to handle both complexity and write fast code. C++ is fast. We have seen in the keynote of Chandler that we can rely on very smart compilers, and the language allows the compilers to optimize a lot. And functional programming helps us at handling complexity. So it pays the effort to unite these two, the language and the paradigm. And even if C++ is not a functional programming language, functional programming is not only a matter of language features. There is people doing functional programming languages there are people doing functional programming in Fortran. So it's not about language features. It's a way of thinking about programming, thinking about problem solving, thinking about the structure of the application, of the software. And C++ programmers can often benefit a lot from thinking in this way. Okay. By the way, modern C++ has introduced a lot of features that help us to use functional programming, even in C++, so we can take advantage of them. Okay. So, let's get started with the first point. The main abstraction of a functional programmer, the main tool is higher order functions. Higher order functions are functions that take other functions as inputs and return other functions. Okay. In the C++ standard library contain, since the very beginning, an example of this paradigm, that is the standard algorithms on iterators, containers, etc., that were not so easy to use at the beginning because we didn't have lambda functions, okay, but the idea was still here. And with the introduction of lambdas in C++ 11, we can officially say that C++ supports the concepts of higher order functions, that we are even encouraged to use functions in this way. So we'll see how, okay? So I'll recap a little bit of syntax because maybe everybody has seen lambdas, so I'll skip rather quickly, but this is how we use a lambda, okay? The sort algorithms take a generic function object, and a lambda is a way to express an anonymous function object in the place where I want to pass it. So in this case, we are using the lambda to sort by absolute values of the elements of the container. This is roughly equivalent to this piece of code. The lambda is compiled into an anonymous type that overloads the operator parentheses. Okay? And only this way of writing it is sane compared to this one. So we can write it, okay? And so, how do I pass a lambda as an argument if every single lambda has a different type? I use a template function. This is a very simple example. The type of the lambda is not needed to be named because we have template parameter, okay? This is, in my opinion, the great feature of C++ lambdas, that they do not introduce any runtime overhead whatsoever, because each lambda is an instance of its own separate type. There's no virtual functions or indirect calls. And this plays nicely with how templates work and how compilers do inlining. We have seen from Chandler's keynote that inlining is very important to C++ performance. And in this example, we can see why. Because this is a template function that take as input an object. This object will overload the operator for the function call, and all of this is completely forgotten in the compiled code. So we can reliably think about this code of being very fast because there's no indirection whatsoever. And this is allowed by the fact that every lambda has its own type, so we don't need indirection at runtime to execute the code. And the inlining does the rest. Okay? In C++11, lambdas had a few limitations. They couldn't have generic arguments. That means we couldn't have a templated function call operator here. Okay. And they couldn't capture variables by move. They could only capture variables by copy or by reference. And the anonymous type can be named, so this means that lambdas could not be returned from a function, but we want to be able to return functions from other functions, okay? Because that's the point of the higher order functions and the single most important point in functional programming. So something we're lacking, and C++14 changed the game because we now have generic arguments, automatic return time deduction, even in regular functions, and generalized capture list, which are very important for a memory management perspective, because functional programming languages often have garbage collectors. In C++, we don't have a garbage collector, so the ability to pass around smart pointers when we capture variables is important, and being able to capture variables by move is important to be able to capture unique pointers, okay? So we said that each lambda object has its unique type. So are we forced to use template function? No. We can use a wrapper, which is std function, which is provided by the standard library, that is a wrapper over any callable object. It is a polymorphic wrapper, so it reintroduces the runtime indirection that we avoided, but this indirection is implemented through type erasure techniques. But this indirection, we have control over when to use it, over when we effectively need the overhead. So, as always, we don't pay for what we don't need, okay? And by the way, this is the same overhead that lambda functions have in any other language, so we don't lose anything, okay? It's important to know when to use std functions versus when to use simple lambdas, because I see a lot of code where people just use std function like as it was the type of the lambda, okay, and they pass std functions around. It's rarely needed. It's useful, but not always, so be careful of the difference, okay? So, after this recap of the syntax, we can see how we can play with functions in C++. Okay, the key ingredients are here: lambdas, automatic type deduction, and templates, and everything else. But C++ makes life more interesting, okay? Because we cannot just pass around objects. We have to be careful with reducing copy and moves operations. We have to be careful handling perfect forwarding if you want to respect the semantics of our objects. So a lot of libraries have born in the last 2 years that may take advantage of C++14. I'll talk about Boost HANA, but you can also take a look at Fit, which is very interesting. And Boost Fusion is a older player in this game, which was very inspiring. And so let's take a look at a little example. The function composition is the first, I don't know, when people learn Haskell, it's the first function they learn even before how to print a string, okay? So function composition is very important in this talk. And we had 3 functions, and we want to compose them this way, so we obtain a function fgh, which is equivalent to call F, G, and H. Okay, I've chosen these types because it reminds me a function to load from a file, a function to parse a string into a vector of floats, and a function to compute something from this vector of floats. Okay, and we want to compose these three functions into one function. Okay, so in C++ 14 it is rather easy. We have a variadic pack. I could have made the example easier by accepting only 2 parameters, but it doesn't make any difference. We have a variadic pack. The base case returns the lambda, which only calls the function. I cannot simply return f because f could be a type that cannot be copied, because if I pass just a function or just it's delicate, so I just wrap it into a lambda, so I know that I'm returning a regular type. Okay, and the recursive step of the parameter pack expansion just call f on the result of the others. Okay, so then this is an example where C++ 14 really made a difference, because in C++ 11 we could not return the value in this way. We had to name in some way the return type. We couldn't even use the decl type return type because the lambda cannot be used in a non-evaluated context, so we couldn't simply write decl type of the body because it didn't work. So we had to rely on explicitly declaring a class to create these function objects, and the code will be more evolved. In C++ 14, we can just say auto, and that's all. Okay, so we really have higher order functions. Okay, a function that returns another function and takes other functions as inputs. Okay, to make other examples, I'll take a look at this library. This is a wonderful library. It's Black Magic, and I will not talk about Boost HANA deeply because it will take other 2 talks. And I'm just picking up one of the core parts of the library, which is a small collection of functional combinators. Okay, so I'll take Boost HANA as the part that provides us functional combinators. Okay, one of the most important is the carrying combinator. A carried function can be invoked with only one argument. A 2-argument carried function can be invoked with 1 argument, and the result is another function that still expects the missing argument. Okay, so this is a function from HANA. Okay, we can pass it a function object, in this case a lambda, and we obtain a function object that can be called in this way. I call it with the first argument, and the result is this is a mistake, sorry, F, S, and T, okay. I can call it F with 4, then the result can be called with 5, and then T can be called with 6, and at the end I'll get the result, okay. Mind the mistakes here, okay. And this is very, very useful when you're passing around functions, because it helps us to reuse functions. If we have a function that is doing some work and we have to pass it around, we can just carry it and pass it around with 1 or 2 arguments already applied. We don't have to write another function that takes only 1 parameter and call the other function. Okay, so we can immediately reuse functions that we already have. This is another very, very nice combinator, which it does not have a counterpart in more classic functional programming languages because it deals with one C++ specific feature, which is function overloading. Okay, and here we are creating a function object from other two functions, lambdas in this case, and exploiting the C++ function overloading mechanism. So we obtain a function f that can be called with an argument of any type, but in any case, it returns x multiplied by 2. But if I call it with a string, it returns the string concatenated 2 times. Okay, it's a contrived example, but it's to give the idea. And these 2 lines, imagine to have these 2 lines in a generic function, in a template function. We don't know the type of the vector. Okay, so this is a way to specialize the behavior of the code for std string without factoring out the code, writing template specializations, etc. It's really, really useful in a lot of places. And this is, it seems, this using line, it seems a joke, okay? Using HANA, nothing, no. It's a very useful combinator that simply allows you to express a simple function that partially applies a binary operator, okay? This is a syntactic shortcut that functional programming languages have always had, but in C++ we will have to declare a lambda that takes a parameter and multiplies it by 2. We can just write like here, and it returns a function object that takes 1 parameter and multiplies it by 2. This works with any binary operator of the language. And it is very useful to write conscious code when combined with other functional patterns. Okay, and there's the most funny combinators from the library is the infix function application. Okay, we'll have an example looking at the home function, which is another combinator again. This is the example from before. The code that I wrote to show the lambda at the beginning of the talk. We are sorting the container by the absolute values, okay? With these 2 combinators, we can write this. We can say, compare, yeah. Compare with the less than operator, but not on the values, on the absolute values. Okay, this is the syntax that you achieve with Bustana for using an infix, a function as an infix operator. The fit library implements something similar, but they use the angular parentheses, with look better to me, but it's the same at the end. And this is just the same thing, but I'm passing a function object called ABS instead of std ABS. You see the difference because the function has to be, I have to state the type of the template instantiation because the template function cannot be just passed as it is. Instead, with function objects, we don't have this limitation because the object has a determined type, and the template instantiation happens at the code side. So the underlying advice here is to prefer function objects over template functions if you plan to use them in this way to pass it around, because it is much easier to pass around function objects than to pass around plain functions. Okay, so and Bustana used this pattern everywhere, even with functions that could have been simple functions or simple template functions. you find instead function objects, because they can be passed around easily and don't have to be explicitly instantiated. Okay. This is the last one. This is very nice to me because it has many theoretical properties and interesting theoretical history behind, but this is called the fixed point combinator. And in this case, it's primarily useful to write recursive lambdas. Okay, we cannot name the lambda. We cannot call the lambda from inside the lambda without capturing itself. It's complex to code a recursive lambda. Okay, the fixed point operator allows us to write a recursive lambda. This is the classic factorial function. Okay, and the fixed point operator factor out the recursive of the lambda, the recursiveness of the code, and let us write a function which is in fact not recursive, okay, because I'm calling this one, I'm calling the parameter, okay, and the fixed point operator handles the recursion, okay. This is very useful. So if there are no questions, or if you prefer to ask them later, I can, yeah.
I have a question. In pretty much every code snippet that you've shown. So in pretty much every code snippet that you've shown, you're passing lambdas and functions by value. Wouldn't it make sense to perfectly forward them?
Yeah, of course. I've chosen to make them simple and not showing std forward in every place. Yes, in the implementation of all of these combinators in the library, they are perfectly forwarded. In the standard library, there's the convention that function objects are passed by value because they are most of the time stateless, so you are not copying anything anyway. And ref and cref functions are useful to force them to be passed by reference, creating a reference wrapper. Okay, so I think that's the answer.
Yeah, hello. Here you are calling a lambda in a recursive way. My understanding of a lambda is an anonymous function. So if you need to put a name on a function that is designed to not have a name, my basic question is, what's the benefit of doing this compared to using a simple function?
Okay, of course. In this example, I could have removed this line. Okay, imagine you have to the most common reason you are writing a lambda is to write in place where you are passing it as a parameter to another function. Okay, so this is a way to directly write it there, the recursive lambda, without factoring it out. Of course, it is useless in this case because I have declared the variable.
Okay, I missed the fact that the first parameter was the.
Yeah. This
I
one,
thought you were capturing the auto.
No, I'm not capturing this. This lambda does not capture anything. This is this one. Okay. Is the parameter. Okay, that's the point.
Okay, I see.
I factor out the recursion out of the. Yeah, I should have removed this line. Thank you for that.
Okay, thanks for clarification.
Okay. So.
If I wanted to do this same kind of pattern in compile time programming, is there a way to get around the fact that a lambda is not const expr?
I don't think so. Maybe somebody. Yeah, in the next version of the standard, they should allow it.
Cool. If I capture the type of the lambda, I can also construct it in C++17?
I don't know, things.
Because that would also be super handy.
Yeah.
If you could move back to the slide with the composition example.
Oh, my God.
A detailed question, because your main point was you have to invoke in the base case f explicitly because you don't want to depend on the copyability of f, but you are capturing f by value, by copy, so you do depend on it, or missing, am I missing something?
Yeah, well, maybe in this case it could work anyway if you pass it a function. Yeah. In this case, it's the same. I was accustomed to ensure that the type is the regular type, because in this case, the template deduction, the type deduction of the template instantiation also decays the type. In other cases, if f is, for example, a function type instead of a function pointer, okay, that is not regular, so you have to either decay the type or okay, yes. In this example, it was not exactly needed. Okay, but well, I go.
Just a note on the constructability of lambda types. They are not. Imagine if a lambda captures something else, how would it capture that again if you constructed it from its type? That's why lambdas are not constructible.
Could you make like an exception if it was stateless?
If it is lambda is stateless, it can be converted to a function pointer, the object itself, but it's still not.
What if that's like default initialized stuff and it's captured? That would be cool.
Yes, but that would be a special case.
Yeah.
And I don't, as far as I remember, C++ doesn't like special casing stuff.
Okay.
They're partial specialized in a partial special case.
Have you tested the performance of Boost HANA? Because we are usually advised not to use std-bind because compilers cannot optimize it out, especially Clang. Chandler is not present. So does the Boost HANA abstractions get optimized out?
I didn't use the library in performance critical code, so I didn't profile it. But the main scope of the library is another one, is heterogeneous computation, type level computation. So performance is a little different topic. But if you just use these combinators, I expect the compiler to have an hard time inlining everything. But in my experience, I didn't have major problems. So std-bind is more involved than these examples because it's very general and very convoluted. These little combinators by themselves are more easily compilable, more easily optimizable, in my opinion. So if there are no other questions, okay. So you have already seen all of this slide. So the next main point of the talk is to avoid mutable state. Okay, one of the main realizations of functional programming is that we don't need to manipulate mutable state when we don't need to share mutable state. Okay, and this shared keyword is very important because in concurrent software, shared state means trouble. Okay, so avoiding altogether mutable state and avoiding altogether shared state is a good way to avoid trouble, in principle at least. Okay, so but why we want to? I already mentioned concurrency problems, but we need to avoid mutable state for other reasons. For example, reliability, because we can write more, we can be more confident on the code that we write by writing pure code. We'll see some examples. And maintainability for more or less the same reasons. And so, but how can we avoid mutable state in a language such as C++, which is imperative and very much imperative? Okay. So the concept is pure functions. A pure function is a function whose result does not depend in any way on anything other than its input values. Okay. We do not access nor share external state, and do not mutate anything. In theory, even internally. Of course, in C++, we can and we have to relax a little on the last point, but it is important to still have the idea in mind. Okay, avoid to mutate things if it's not necessary. Okay, why? Because purity helps us to avoid to have action at a distance. So effects that comes into existence in other parts of the universe without any apparent reason, and just because you have changed something here. Okay, this helps us to separate the concepts. Okay, separate the computation. That means what our code is supposed to do, to compute, to manipulate, etc., from side effects, which is write them, transmit them, read them, load the inputs, communicate the outputs, etc. Why? Because pure components are easier to compose, and we will see a lot of examples of this item, and easier to test, because we can repeat the execution of a pure component as many times we want without resetting initial conditions, without care about the environment, okay? And are inherently thread safe, because they do not access shared state, so race conditions are impossible. And we'll take a look only at the first point, second actually, the composability of pure functions. What does it mean to be composable? If I not define the word, it will sound like a way to sell something. It's not. This is the definition that I have in mind. It's not the definition of composability, nor the most used definition. It's just, to me, a good definition. Okay. When you ask yourself, is your code is composable? You have to ask, if I have two good components, substitute good for anything, fast, correct, thread safe, good looking. Okay. If you have two good components, is their composition, so the system that results from putting them together, is still good? It's still fast? It's still thread safe? It's still correct? Okay. If the answer is yes, you have two composable components. Okay. So we are looking to write code and to write C++ code in this way, to have composable components. Okay. And I picked a very simple example. One of the first higher order functions that people learn when learning a functional programming language is the map function. Okay, the map that takes a sequence and applies a function on each element of the sequence, returning back a sequence with the values transformed. Okay, in C++, in the C++ standard library, it is called transform, and it works like this. We give it the pair of iterators of the input sequence. the output iterator where to write the results, and the function object. Okay? It is simple. Is it fast? It is fast because inline works very well. But there's something that looks not all right here. What happens if I have to change the type of the result? That is, I suddenly return something different than an integer, so I can write the result into a vector of integers. Or what if I want to chain more than one of these transformations? What happens? So let's look. This example won't compile because toString returns a string, and we can write strings into an output iterator from a vector of integers. Okay, so I have to declare another vector of the right type. And what's the problem? We have to manually manage the memory, not strictly speaking, but it's what we are doing. We are allocating the result, okay? We are declaring the result. And we have to repeat 2 times the type of the inputs, 2 times the type of the output. We cannot automatically deduce this type from the return type of the function. And here I can write it, but in a generic context, it could be impossible to tell. And I have to manually manage the size of the result container, or in this way with backinserter, which by the way is awesome, but or resizing the container before. It's clear that something is missing, okay? So can I compose 3 of these calls? To call STD transport 3 times, I have to declare 4 containers, backinserter all the place. It's terrible, okay? So the answer to the questions that I posed before is no. I have fast, clear, readable piece of code, and I cannot compose it into a fast, readable piece of code. It's not even fast anymore because all of these passes are allocating memory, going around with pointers, iterators. It's not the same, okay? It's not even faster anymore. So what's the problem? The main problem here is, so why should I prefer the functional way over a classic imperative loop with pushback? It's easier, right? Okay. So maybe it's the wrong use case for the function. No, it's the wrong function, okay? And the problem is that STD transform mutates its inputs. This parameter, the third parameter, is an output iterator, is the moral equivalent to the output by reference parameter, okay? The problem is here. So we can solve the problem by redesigning how the function works. Of course, we cannot return a new vector, okay, because the performance will be awful. So as most of you probably already know, the solution to this problem is by designing this kind of functions, these kind of algorithms, over the concept of ranges instead of pair of iterators. Okay, I'm not going to delve into details of the ranges library because there are at least 2 or 3 other interesting talks at this conference about the ranges and related topics. but I'm going to use them, okay? And I'm going to look at the ranges V3 by Eric Niebler, which is really, really wonderful. The library, but also the guy, I think, okay? So that's how it will look with ranges, okay? We can chain transformations because we are returning the lazy views, the ranges views, okay? But actually, this is how it looks because we have the nice piping operator overloading, okay? So we can clearly state what are the steps of the computation. We can compose 3, 4, 5, 100 transformation without risking anything, and the result is still fast, okay? How can this be faster than this one if it's doing the same thing? I mean, it's only a syntactic difference, or there's something more. Of course, it's not only a syntactic difference, okay? Because ranges views are lazy, okay? And we are going to step into the third main point of the talk, that is laziness, okay? That means that each element of the result sequence is computed only when needed, okay? Intermediary ranges are never completely built, never, okay? You will not ever have a container or a temporary result in memory with the result of the second application of transform that is fed into the third application of transform, okay? The result is the same title loop of the imperative code that I showed you earlier. This I personally saw this in practice, so with regard to Bustana, I can say much about this. And of course, that means that on my computer, only to include the ranges library headers, I have to wait 6 seconds. But the compiler, I don't pay the compiler for an hourly rate, so it can work. So, we want to be lazy. Laziness is one of the reasons why purity it does not compromise performance. And it's possible because of purity, because pure code does not depend on the order of evaluation. So it does not matter if I compute a function before the other or vice versa. Most non-pure functional languages support laziness in some way or another, even if side effects are allowed in non-pure context. It is always better to limit side effects. So in C++, we can launch missiles in lambdas, but it's still better to not do it. And as with the ranges library, we can implement ad hoc laziness in C++ where we need it. There are a lot of libraries that do it, from ranges to the Huygens library that Chandler mentioned this morning. Okay, so this is one example. With laziness, we can create infinite sequences. We can have infinite sequences of random numbers in this way. For example, I'm capturing the standard random number generator and calling it at each iteration. And the generate function will generate a sequence, a lazy sequence, where each element is the invocation of this lambda. Okay, so what I get is a function that effectively is returning me an infinite sequence of random numbers. And I can pass around freely this sequence because the sequence does not really exist, okay? And I can pass it around. And for example, I can do simulations of the first, using the first 10, the first 100 random numbers as inputs this way. You see that it's very clean, it's very composable because I had written one time the random numbers function. I suddenly don't want a vector of random numbers. I want something else, or I want more or less numbers, or I want to iterate over each number instead of collecting them. I don't care. I can still write we use the same function as before. I don't have to modify, to change the code of the function to make it suitable to the using pattern, okay? And this is another example. We have two functions. Imagine a function that creates or computes a vector of integers, and another function that takes this vector of integers and computes another result. It is a contrived example that represents a very common pattern. And imagine that you have spent months in optimizing this function and optimizing this other function, probably written by separate teams, different people, okay, different libraries altogether. But you know that the two functions are very, very efficient and very optimized. And then you want to simply take the result of one and use it as input to the other, and you obtain horrible code because you are allocating a huge vector probably and feeding it to the function which is retraversing it again, okay? And it's probably not horrible, but certainly is suboptimal, okay? So imagine instead if you had a range-based solution. So you have the very efficient source is now returning a range type, a type whatsoever. It doesn't, we don't need to know which type it is. The sync function accepts any range, okay? So you can still write and optimize the single functions. And now the composition, which is the same code as before, suddenly the naive way to compose the functions is also fast, okay? Because we are lazily creating the sequence and we are lazily consuming the sequence, okay? And we do not waste anything, okay? And note that the single functions, the single two functions, can be still coded in isolation. You can still have two different people, two different teams, two different species writing the two functions, and you can compose them, and without modifying them, without change anything, you get the composition right. Okay, so I have two fast components. Is their composition fast too? Yes. So we have composability. Okay, and this is thanks to the laziness of the ranges. Okay. I open a parenthesis here about functional data structures. Purity and laziness are also very useful in designing data structures. Of course, we need data structures to do useful work. And to write pure functions, I need the pure data structures, which means that, for example, a container which cannot be mutated, but I can add an element to the container and I get a new container, which is the same as the one before, but with an element more. This, of course, means that the containers have to be implemented and designed in a totally different way. So this opens a whole field of computer science, which is totally out of the scope of this talk, but it's very interesting. And the persistent data structures, which are often called, are very useful also in a non-functional setting because they made concurrency and lock-free programming much easier, because the sharing is controlled and we don't mutate anything. Okay. So I'm a little late, so I'll skip rather quickly on this. Another point that I would like to take is that we have a very strong type system in C++, and functional programming encourages to use types to model invariants, to make the compiler help us to write correct code. Okay, in functional programming languages often implements what is called algebraic data types. Okay, algebraic data types are the most natural way of thinking about types in a functional setting. They are called algebraic because they are built from, an algebraic data type is built from simpler types using free operations. So we can remember the algebra, okay? And the sum of types is a type that is made of values of one type or the other. The product of the type, or of two types, is a value composed of both a value of one type and the other. And then the exponentiation is just the function types, okay? You can see why they are called sum, product, and exponentiation by counting how much values of your type there are. Here it's the sum, here is the product, and it's t2 to the power of t1, okay? This is abstract, and I think it's not abstract. We can have algebraic data types in C++. STD tuple, or any struct or class with fields and members, is a product type. We have a lot of sum types that are very useful: boost variant, optional, expected. Okay. Boost variant is a sum type, generic sum type over any number of types. Optional is a sum type that is t plus a singleton type, and expected is a sum type t plus e. Okay. And abstract data types are often may seem to cover the same use cases as inheritance hierarchies. Okay, because also in inheritance hierarchies you have a value that can be of different types. You don't know which, but it's actually the opposite of each other, because class hierarchies support a fixed set of operations that are the virtual functions that you have declared over an open range of possibilities, because anybody can derive the base class adding a new possibility, while some types support the opposite case. You have an open set of operations, that is any function that accepts your type as an input, over a fixed range of possibilities, that is the number of components of the sum type. Okay. Probably each time you need to apply the visitor pattern, you probably needed a sum type if the language supported it, probably boost variant or something like this. Most often this is the case. And a language supporting abstract data types should support pattern matching. If you have programmed in Scala, in Rust, in Haskell, you know that pattern matching is awesome. And we don't have pattern matching in C++, and we don't still have a good library solution for it. But there are the alternatives or equivalents, and there's a nice library from Strauss-Troop. It is really, really, really black magic, but with macros. Okay. So if you want, you can take a look at it. And this is an example of the use of algebraic data types to cover the problem of error handling. Okay, we want to handle errors in our code in a reliable way, efficient way, and readable way. Readable means that the mechanism does not clutter the code too much. Okay, and exceptions are great, but there are limitations. And the most important one, being quickly, is this. There's no way to prevent a programmer to forget to catch some exception type. So there's a reliability problem. Okay, and there's also an efficiency problem if the non-exceptional path is taken too often. The exceptional path, sorry, is taken too often. Since we have 0 overhead on the non-exceptional path, but the other path is lower. Okay, so just use them to signal exceptional events, but it's hard to say if an event is exceptional or not. For example, if you have a parse function, you can say, well, a parse error will be common enough to not be considered exceptional. But it could be that this function is called after other code that guarantees that your string is not malformed. Okay, so you could happen that you have an invariant in your code and you call this parse function only on well-formed strings. So we cannot say a priori right in the parse function if the parse error is exceptional case or not. So, okay, so, well, we're talking about exception during the coffee break, okay? And this was an exception, okay? So, well, the bottom value, use std optional for error handling if exceptions are not okay. Okay, and then I had to talk about lawful abstractions, but I'll just skip this this part. Just say that if you are curious about monads, follow the talk from Ivan, which is talking about this this topic tomorrow. I just wanted to point out that a monad is just a way to abstract of the same operation over different types. And so this is another common pattern in functional programming, to look at patterns in code and abstract them. Okay, so I'm sorry for the deadline, the missed deadline, but thank you.